All right, we're going to take a look here at the derivative of inverse functions. Now, to do so, we're going to first consider the relationship between a function and its inverse graphically, and use that to understand the relationship between a function's derivative and the derivative of the inverse of that function. We'll write out exactly that relationship, both in words, and then we will construct a formula to make it more concrete. So the function we're going to consider is the function e to the x, and its inverse, which I will call g of x to make it easier notation-wise. And the inverse of e to the x is, of course, the natural log of x. So let's go ahead and take a look at the graph of both functions. So here's the graph of f, e to the x, and when we look at the graph of the inverse, we simply need to reflect the graph here over the line y equals x. So here we have the graph of the inverse, and while it's easy to sketch this curve here once we write the line y equals x, I want to make it very clear what happens to each point. So it's very easy to see here when you look at the y-intercept of f. That point reflects across the line y equals x and goes from being the point 0, 1 to 1, 0. Right? In the concept that we first learned for inverse functions, you're switching the role of the input and the output variable. So it makes sense that when you go to the inverse, the x and the y coordinates are swapping. And that is occurring for every point. So any point on the green curve is reflected across to the red curve by switching the x and the y coordinates. And that's going to be really helpful in understanding what happens to the derivative. So let's pick a point on the curve f, and we'll take a look at where that point went and try and see what can we tell about the derivative at the point on the green curve and the point that it reflects to. So here's this point at random. It has an x value of a, as I've denoted on the x-axis, and a y value b, as denoted on the y-axis. Now let's take a look at the reflection of this point over the line y equals x. In other words, the point that corresponds to this point on the inverse. So here is that point, and of course notice that the x-coordinate is b and the y-coordinate is now a, since it is the inverse of this point over here. Now our goal is to look at the derivative, so let's first consider the derivative at the point AB, and let's remind ourselves how we compute the derivative. What we're doing is we're looking at the limit as the distance between 2 points gets smaller and smaller of the average rate of change. In other words, we have some point over here, and we compute the average rate of change. And we keep doing so as those 2 points get closer and closer together. And when they're infinitely close together, right, the limit as the distance between them approaches 0, we're getting the instantaneous rate of change at this point. So let's go ahead and just represent a point here that we can use to visualize what our calculation for the derivative is doing. So here's our point, and we want to visualize what makes up the derivative. And that, of course, is going to be the change in y over the change in x. Now, as this point gets closer and closer to this point, the change in y over the change in x, they both become infinitesimally small. So we refer to them as dy dx, as I've shown here, and that allows us to name the instantaneous rate of change right at this point, and it'll help us visualize it with the little tangent line here, and that is the value of dy dx. Okay, easy enough. Now what we're going to do is analyze the derivative at this point, and to do so, let's actually take the reflection of the point we used over here, bring it over to our red curve, and that will allow us to analyze in exactly the same way the instantaneous rate of change at this point here. So here we have our point, and now we're going to analyze the derivative at the point BA in the same way that we did the point AB, by visualizing the change in y and the change in x, and thinking about them as the distance between the 2 points approaches 0. Alright, so we now want to consider how this derivative here, these two components, are related to the components that we use to compute the derivative at the point AB. And at this point, you should probably see it, and you should also be thinking about the slope of this tangent line versus the slope of this tangent line, and it should all be clicking. So notice that the point here has a y-coordinate a that is the x-coordinate of this original, its corresponding point, AB. And this point here has the y coordinate that was the x coordinate of this green point over here. So when I'm computing the change in y between these 2 points, or in other words, dy, that's the same computation that goes into dx between the green points. And the change in x between these 2 red points is, of course, the same computation that goes into the change in y between the 2 green points. And so there I have my relationship. Nothing more than a reciprocal relationship. Whatever the slope is, or the derivative is, at this point, a, b, the point BA has a slope that is exactly the reciprocal of the slope over at AB. And so this tells me exactly how to evaluate the slope of an inverse function. I simply need to go back to the point, the corresponding point on the original function. I need to compute the derivative there, and then take the reciprocal, and that gives me the derivative over here. I'm going to draw that tangent line so that we can see this here. It's very easy if I just analyze the slopes to see that the slope here maybe looks like it could be 2, and the slope here is certainly more shallow but still positive. I could make the easy visual argument that it's 1/2. So I'm going to put this into words now so that we can build not only a visual framework but also a verbal framework that we can remember potentially more easily. Now the way that I remember it verbally is I think to myself, the derivative of the inverse of a function at a point is the reciprocal of the derivative of the original function at the corresponding point. So in my mind, I visualize the point on the inverse function. I realize that I want to go back to the corresponding point on the original function, find the derivative at that point, take the reciprocal of it, and that is the derivative that I'm searching for. All right, so now let's take our verbal understanding and our graphical understanding and use it to create an algebraic formula for finding the derivative of an inverse. What we're going to do is sort of just piece by piece take this verbal argument apart and represent it algebraically. So let's start with this, the derivative of the inverse of a function. So what I'm going to be doing is taking the derivative, in this case with respect to x, of my inverse function, which I can denote like that, or a little more succinctly. And notice, of course, that this is the symbol that represents the derivative. Okay, so let's keep it going. What we need to do is to find the derivative of the inverse function at a point, and the x value of that point is x here. We need to take the reciprocal of the derivative of the original function at the corresponding point. So let's think about what we need to do. We need to get to this corresponding point, and then we need to take the derivative at this corresponding point, and then we need to take the reciprocal of it. So if we are at this point here, how do we go to our corresponding point? Well, think about it. We were given the x value, or in other words, b. What we need to do is evaluate the derivative of our original function, not at b, but at a. Because a, the y value of our inverse function, is the x value of our original function. How do we find a if all we have is b? Well, if we know the inverse function, we can just evaluate it at b, and that will give us a, which is, of course, the x value of the point on our original function where we want to evaluate the derivative. A lot going on here. I'm going to represent it this way. To find that y value that we seek, we're going to evaluate the inverse at b, like that. So here, I know that the x coordinate on my inverse function is x. So I'm going to evaluate the inverse function at x, and then I am going to evaluate the derivative of my original function at that value. So that's going to look like this. F inverse at x, that is giving me, this piece here is giving me the y value for the point at which I am on the inverse function, which is the x value on my original function. So now that this is the x value at which I want to evaluate the derivative for my original function, I need to do so. So I will take the derivative of at this point, of my original function. Now notice I'm writing this down here because I need to take this derivative and take the reciprocal of it. And the easiest way to take the reciprocal, just to write 1 over that value. And so that is how you compute the derivative of an inverse function. This takes a little while, this formula here takes a little while to wrap your head around. And even though I've spent countless time looking at this and using it in my life, I still prefer to think about the graphical representation, and I use my verbal understanding to make sense of whenever I'm taking the derivative of an inverse. What I would do right now is go ahead and go back to the last practice test that we took. Go to problem number 92. Problem number 92, and try that problem out now. And you should have a much easier time with it. You might even draw yourself a little visual to help you with that and work through it. If you want to stay here, what I'm going to do is a quick little example to help cement why this makes so much sense. So what we're going to do is take the derivative of the inverse function evaluated at 2. Now, visually, I understand what I'm doing. I'm going to go back to the corresponding point. I'm going to take the derivative of the original function at that corresponding point and then take the reciprocal of it. What I'm going to do to compute this is use the formula that I have here. So I realize that it's going to be 1 over. I'm going to take the derivative of my original function at the point f inverse of x, so f inverse of 2, which is the y coordinate on my inverse function, and of course the x coordinate that corresponds to it on the original function, where I want to take the derivative. So f inverse is natural log of x, so it's going to be natural log of 2, just like that. Now, f prime, since f is e to the x, we know that f prime of x is also e to the x. So going down here, I realize that this is going to be 1 over e to the ln of 2, and e to the ln 2 is just 2. So this is 1 over 2. And of course I know that to be true because I know the derivative of natural log of x is just 1 over x. So the derivative of natural log of x at 2 is 1 over 2. And sure enough, that's what I get using this formula here. All right, I hope that was helpful. If you have any questions, please make sure to ask.